Hello everyone, let's begin Chapter 6 exercise set. For this exercise set, we need some additional resources. First, we need, of course, the exercise set itself. In addition to that, we need something called a normal table or the z-table. Here we are looking at the course content folder of our class page, and scroll down and you'll see stat tables. I posted a bunch of tables. Some may not be used, but the very first one is going to be used a lot from chapter 6 until the end of the semester. And this is what I'm talking about. This is called the normal table, and this curve is called the normal curve. It is traditional to use the character z for the normal curve, so very often we call this z-curve and z-table. Here's the first page, and here's the second page. It's going to be a good idea to download, save, and print out if you haven't already. If you did all those, then you're ready to start Chapter 6 exercise set. Let's go. A radar unit is used to measure the speed of automobiles on the expressway during the rush hour traffic. The speed of individual automobiles are normally distributed with a mean of 62 miles per hour. Okay, here's the first problem. If the standard deviation is about 4.95 miles per hour, what is the proportion of the cars that are traveling in 70 miles per hour or less? 70 or less. This is normal distribution problem, so we start with the normal picture. It looks kind of like this. The outline is pretty simple, going up and down, unimodal and symmetric, and we have asymptotic behavior to the left and to the right, and center is the mean, 62 miles per hour. Because this is asymptotic in the left and right, there is a probability according to this normal distribution that cars are traveling backwards, that is, having negative speed, or even worse, traveling faster than speed of light all the way toward the right hand side. Of course, those kind of probabilities are so small that they don't really make any kind of sense in real life. Everything in statistics is approximation, so those kind of strange artifacts do exist, but that's the nature of statistics. Okay, we talked about the outline and the center. Now, step 3, the end of the shaded region. The problem explicitly said 70 miles per hour, so where is 70? 62 is down here in the center, and 70 is greater than that, so you have to go a little bit to the right. Final step, shade. It says 70 or less, so or less, in number line, less is left hand side, so you shade the left hand side as this picture. And this is the step-by-step process. Outline, center, end, and finally shade. You follow this step, and step 1 is complete. Drawing a picture, the very, very important step. If you do not draw the picture and try to do something, and if you do everything right, if everything is right, then I may not take off any point, unless the problem explicitly says justify with plot. But there's a big chance that you make some mistake here and there. Then if you don't have any picture, then you're not going to get any partial credit. That can be rather devastating in the exams when each problem counts like 10 points. And just a little mistake, instead of something like 8 out of 10, you get 0 because you didn't draw the picture. That can be rather very, unpleasant experience. Okay, now that you have a picture, let's go ahead with the solution. This problem is based upon the formula number 1 of this entire course in the level of important, this one. Z equals x minus mu over sigma. But this formula even though it is very important, is rather impractical because it can be confusing. Depending upon circumstance, we may use different character in place of x. In place of mu, we're going to use something different. Sometimes for the numerator, you may use mu minus x instead of x minus mu. And denominator may be something different. Even though we have the same structure, they can be rather confusing. Here is much more practical way to get this done. Z equals to end minus center over SD. SD for standard deviation. Now for chapter 6 we use SD. From chapter 7 and on we're going to be using SE, standard error, in place of SD. And this is the formula number 1. Here in chapter 6 we're going to stick to just the standard deviation. Now how does this formula work? Well, what is the end? 70. What is the center? 62. What is the SD? The problem said 4.95, so that goes to the denominator, and that's how we get this computation down here. If you use your calculator, you're gonna get 1.616 something, so approximately 1.62 is the approximation of the 2 decimal digits. Here, this computation was done with Mathematica. I use technology based upon something like 12 or 13 decimal digits. So this is really accurate answer. But our normal table is based upon just 2 decimal digits. So let's use 2 decimal digits, 1.62. Now, how do I utilize my normal table here? 1.62 is what I want, and the values are in the left-hand side column there, and all those are negative. You have to go down to the second page. 1.6, where is 1.6? Here's 1.6. And the second decimal digit was 1.62, wasn't it? 2 was the second decimal digit, so you have to look up the second decimal digit, 2 column here, third column. I almost said second column, sorry about that. Third column is 2, beginning from 0, 1, and 2. And go down, and here we are. I already highlighted 0.9474 is the desired probability or desired proportion. According to this normal table method, we got 0.9474. About 94.74% of the cars are driving in 70 miles per hour or less. Compare that with Mathematica's computation here, 0.94697, very close. Of course, they're both approximations, and we're gonna just approximate it further, estimate it further as 95%. About 0.95 or 95% of the cars travel in 70 miles per hour or less. Let's summarize. Draw a picture, outline, center, end, and shade, and z-score computation, end minus center over SD, calculate and get up to second decimal digit and look up the table. That's how we get the probability of the shaded region on the left hand side. Okay, do we have enough time for the justification? Okay, looks like it. So we'll justify what we just discussed. Now, this is for interested students only. So if you're just barely following step 1 and step 2, stop this recording and don't go any further. Just go to the next recording. Now, justification. Why did he look up the z-table? Why did he calculate the z-score? Well, here is a justification. We have 2 normal pictures. identical as a matter of fact, except for the scaling. Here, centered at 62 and 70 or less. And this is the picture we saw before. Here, right hand side, we have exactly the same picture, colored differently in green, but centered at 0, and the standard deviation in this case is 1, whereas this one has standard deviation at 4.95, and it begins at 1.616 something, the z-score. This area, blue area, and this area, green area, are the same because z-score is nothing more than a kind of rescaling. Here's my analogy. Consider a temperature given by Fahrenheit. That's blue. And how do you rescale it into Celsius temperature? Well, Fahrenheit minus 32 over 1.8, and then you get Celsius temperature, and that is standard one right over here. But we are talking about just same temperature, just measured in different units. Here we have Fahrenheit, the usual one. Here we have metric system. Likewise, we have this current situation, 62 miles per hour is the center, and 4.95 is the standard deviation, and so on, versus the standard normal picture, centered at 0, and standard deviation is 1. And what is generating this transformation from blue to green? That's where this formula number 1 is coming into play. That's where I'm going to stop. As a matter of fact, proving this using some calculus is going to be discussed in 3000 level math course. So for this justification, I'll stop here. Okay, so much for the justification, and we're going to discuss the second subproblem in the next segment of the video.